We'll talk about structure for just a little bit here. The idea is that as we're working, we're putting all this fantastic work into building this nice architectural model, but actually you're putting a lot of information in there that could be used for structural analysis. And you really, not like to have two different models, you'd like to have a single model and be able to use all your hardware here, and it should do that. So if you put in a beam or a column or something, we can actually go through and compute the loads on that column, the loads of that beam, and size it all. It's really an active model for analysis, as well as for documenting your design intent, so both. So we're going to, as we move on through the course, start playing around with that, where we're going to use Revit, what we've been using for our basic modeling the elements, and we're going to show you how you can go through and tie that into structural analysis tools. Within the Autodesk suite of products, there's something called robot structural analysis. There's a web-based version as well as kind of an application version that's installed on these machines. If you're a structure student here in the Stanford CEE department, you're probably used to using e-tabs. Okay, and we could also send these things to e-tabs if you're already very familiar with that. It doesn't really matter what analysis tool you're used to. You always can take the model elements, take them out to the analysis tool, whichever one's most familiar to you. Do your work in the analysis tool, then you take your work from your analysis tool back into the model. And the idea is you shouldn't be losing work. So the Revit model should be generating the model for analysis, and any design work you do in the analysis tool ultimately should send back to Revit, so that if you change the beam sizes, that's actually reflected back in your building model. So it's really a very nice workflow. And I just want to give you kind of a quick introduction to it, because it sort of gets to this issue of really how we actually go to the next level in terms of our modeling and we start thinking about structure. So I'm going to build a real simple little model here. And again, if you need to be continuing to finish up on your assignment, keep on going that way. I don't care. I won't be offended by that. If you want to watch out of the corner of your eye, or watch very intently and try and follow along, whatever's going to be most appropriate to you. I want to be respectful of your time. So I'm going to go through and create a very simple little model. If you just want to watch me do it, that's A-okay in terms of what's going on. You don't have to follow along if you're working on your own project right now. But it starts like this. Let me just finish that up and go through and create a new model. I'm actually going to go through and create something out of the structural template, because it's going to have some things built in that'll make my life a little easier. Okay, what I'm going to do is actually start creating a little frame structure, and just to give you an idea of what I'm trying to create. In most buildings, I go through and I'm just going to make it a very simple little rectangular building like this right now. I have a little structure, and within that structure, to support that roof, things may be supported by the outside walls, but very commonly we'll have some columns in here that are coming up from the ground. In a structure like this, there might be 6 of them. And then between those columns, we're going to have some beams that are supporting things. And then on top of that, we're going to have a little bit of a roof. But often there's a structural system that's supporting everything. It's not just the walls. And as we move from residential construction, where things are so small, we can depend on the walls, to more commercial construction. Often our buildings are built really in terms of the structural frame, and then the whole issue of the walls becomes more an issue of a skin, a glass skin or a stone skin. But we tend to build the structure first and then just sort of build the skin on top of the structure. So it's kind of like the skeleton of the body. It's the bone structure underneath it all, and then we learn to sort of skin it. We tend to think about buildings that way. So I'm going to start with today just this notion of how you build a little structural frame. And we'll build a very simple little structural frame that we'll then start adding some skin to. Okay, so it's going to look something like this. As I go working to go through and build something like this, and we're building bigger buildings, it's very helpful to go through and actually have some sort of referencing system. So just so we understand, how things are organized, it's very common to say this is a grid line system of A, B, C, and maybe 1 and 2 over here. And what a grid system does is it just gives us a very nice way of referencing things. So I can say that's column C1, that's column B1, that's column A2. It's just really a reference system. And it's much easier than saying the column in the upper left-hand corner, because then we could all talk very, very precisely. So it often starts with putting in a grid system, then putting columns on the grids, then putting beams between the columns, and then finally putting the floor on top of it. So that's the general flow of what we're going to do just right now for you. And that's kind of the way we build it. So let me show you what that looks like. In the Revit tool, under the Architecture tab, we've worked with levels before, but I'm going to use something called the grids. And I'm just going to go and draw a grid from left to right. That's going to be grid 1. That's going to be grid 2. So just kind of creating a very simple grid. What I'm going to do is in the other direction, I'm going to pull on down. Now, it's going to guess 3, because what it always does is it increments. It always goes to the next number. But if I want to switch over to an alphabetic system, I'll just change that to A instead. Zoom out. And then when I put my next grid in, that'll be B. And the next one will be C. And I can adjust these, push them all around, kind of make nice even spacings. You'll find that in buildings, they tend to be very nice and evenly. Let's say that's like 30 feet from that grid to that grid. And maybe in this direction, I'll make it 30 feet that direction, and 30 feet over here. But we tend to have very nicely organized grids to line everything up. And that's just the starting point. Okay, so let's pause there for a second. Does grids kind of make sense? Most of you, I think if you've done any structural modeling, you're probably used to seeing grids. Yes?
In your modeling, you build a structure, modeling, you create the structure part first,
yeah. What tends to happen is we'll come up with sort of an overall sense of how big the space should be. And usually we'll start by putting the grids and the structure in and then sort of building the building around it. You sort of end up converging in the middle. Oftentimes you'll sort of draw a lot of the structure or the skin, but you'll have a sense of where the grids are going to go. Yeah. More often than not, in houses we can sort of just make it up as we go. When you start with, if I have to put together 100,000 square feet of building, we tend to start out with a pretty organized top-down approach. And if we go with that, we typically start by laying out the grids and try to figure out there's going to be 10,000 square feet of this on that end of the building. There's going to be 20,000 square feet of that on that end of the building. So yeah, it definitely, we tend to start in a much more organized way. Yes?
And grids can be said as an array? Or?
Again?
No, grids can be said as an array.
Oh, yes. So, yes, you can array them on down linearly. We can array them as an arc. Either sort of way of doing that. And that's actually not a bad way to do it, because if you do them as an array, then if you change it, they're all going to change the same distance. Yeah, so that's a very good way to do it. Okay, so once you've placed the grids, the next step is actually to put some columns on here. Okay, and the columns are actually pretty straightforward. Columns are really just the library part. Actually, talking about what we did a little while ago, columns are an example of a sweep. Because the way columns work, you don't think of them as an extrusion if they don't have a bend in them. Columns tend to have, if they're a steel column, a very specific profile shape that's just kind of extruded in a direction. Okay, so the whole steel catalog is out there. All the detailed kind of profiles of exactly how thick the flanges are and how big the web depth is. That's all available. But when we're placing columns, you go to the Structure tab. You choose the Column tool. And they have a couple of standard shapes in there right now. There's a concrete column and a wide flange column in there. If you don't want these shapes, we can load in some more. We'll show you how to load in some more wood or concrete columns or wide flange columns. These are some standard profiles that are available. If you need to load anything, we can load them in from the library. They live in the Structural Columns section. And if you go to like the wide flange columns, you'll see there's really the whole catalog. The whole steel catalog's in there of all those different things. But I'm not going to worry about loading them right now. We're just going to start placing some columns for what we're doing here. In terms of placing, let me warn you about one very funny difference in the way people view the world between architects and engineers. When you talk to architects and you're placing things on level 1, they tend to be thinking about level 1 and things going up from level 1. When you talk to structural engineers and they're thinking about level 1, when they're placing columns, they're typically putting columns below level 1 to support it. Okay? And that shows up right here. There's a choice here as we're placing this column. Are we placing them depth or are we placing them height? Either way. So just be aware of that. You could always change them later. It doesn't really matter. We're just sort of whatever convention makes the most sense to you. I'm going to put some things, I'm going to go for the architecture scheme. I'm on level 2 right now. Let me go to level 1. If I was on level 2, I'd put them down. I'm going to go to level 1 and put them up. From level 1 to level 2. So I got some columns here, and you'll see that really I could place my columns by just placing them like one at a time. I can sort of hit the little space bar and rotate them around, but I'm going to put it right there. I can put one on this one right here, and I can keep on doing that way. Let me show you there's actually kind of a very quick shortcut though. And again, don't worry if you can't follow along keystroke for keystroke with me right now. Just kind of sit back and get the general feel of where I'm going, in that they have this notion of a way to put a lot of columns in, and that's sort of a common thing. If you've got your grid set up, it turns out almost always your grids and your columns kind of line up with each other, your columns line up with your grids. So the way they accommodate that within Revit is you can actually say, let's just go ahead and place columns at the grids, and then I can choose different grid lines. I'm going to control click to grab a bunch. And what happens is that all those grid locations, it's going to suggest putting a column. Okay, so it's just kind of a really quickie way to get your columns. If you put your grids down, it'll place columns right at the grids for you. And that just saves you some time. Let me finish to put them in there and show you what that looks like in 3D. So I got something that's looking like this. Just 6 columns kind of hanging out there. It's the beginning of my structure. Not too awfully bad. Let me check to see. Did I get 2 there? No, it was actually smart enough. Didn't put a second one there. So columns is where this all starts. And again, I can change the type of any of these. It's just type. So the same way you change the type of furniture, you change the type of floor, you change the type of a structural element. So if a specific column wants to be a different size, I just change its type. Okay. Next up in the scheme is the whole idea of putting the beams in between. Beams are again sort of a type. We go through and choose the beam tool, and we're going to indicate the endpoints for the beams. And typically I just snap on the tops of the different columns, connect them together. So it's very much like doing an erector set or some sort of tinker toy. We just tie everything together. I'll choose beams. I'll choose some specific type of beam, and they have some standard ones in here already, but we could load in some new ones. And what I tend to do is actually I'll say I'm going to place it at level 2, but I'll use 3D snapping, which lets me then just kind of snap to the tops of those things. So that's kind of a quickie way of doing that. Now I could put them in the floor plan view. One of the tricks about putting beams in the floor plan view is when you're putting in beams and you're on level 1, you're typically putting the beam above your head. This is where the structural engineers actually have it right. Because in a floor plan, you're looking down. You should actually, it probably makes more sense to put the beams on the floor below you than the floor above you. Okay. But in 3D, it doesn't really matter. We can sort of see it both ways. So I'm going to put the beams at level 2. They're not going to show up in the floor plan view. They show up in a ceiling plan looking up. Then, I have to go to level 2 to look down and see them. But I can put them in here. Now, in the same sense of there being shortcuts, remember those grid lines were really handy for putting the columns in. Turns out grid lines are pretty handy for putting beams in too, because very often you put beams on the grid lines also. Okay, so I can place them all individually, or I can do this thing where I say, let's go through and put the beam in. And white flange there. It's kind of hanging off the end of the menu. Oh, I can't do it in like a 2D. I do it this way. Or in 3D. Beam on grid. So I'm going to place the beams on the grids. I'll say on grids. And I can actually just choose that grid, this grid, this grid. And when I finish that up, you'll actually see that's actually put a lot of beams in there. Again, I'm rushing through this real quick, so don't worry. We're going to go through this in more detail later. I just want to sort of give you a preview of where we're going. Control Z, we're out of there. Okay. So now I got this sort of interesting structure. Kind of looks like this structure over here. Not too hard to model it this way. It really is just like building up, just like Tinker Toys or something like that, building up the blocks. Last thing we're going to do is actually just put a floor on this. Let's talk about that. Now, steel construction, I'll warn you about, it's just a little bit unique in that one nuance I'll kind of share with you tonight, and again, we'll look at this more later, is if you think about those steel columns and beams, we actually don't put the beams at the top, the full floor height. We actually, for steel, need to lower them a little bit. There's going to be a concrete floor deck and a little bit of steel decking. Like, if you're in the site room, look up at the ceiling, you can see the concrete decking. You actually see the steel decking with the concrete on top of it. Yeah. But we tend to actually have to lower these just a little bit. So there is this notion of depressing the beams. Let me show you what I would do with that. I'm just going to grab all the beams. And as opposed to having them right at the floor level, I'm going to give them a little bit of an offset. It's called a Z offset. I'm just going to lower them down 5 inches. And why am I lowering them down that 5 inches? Because the concrete deck and steel is about 5 inches. So I'm going to just lighting underneath it. So I'll say lower that down. Okay, so just in terms of true construction technology, that's a little bit closer. I tend to have those a little bit lower. Don't worry about the fact you don't see any haunches or braces or any welded connections. We'll add those in again later. Analytically, this is going to work. These lines that you see in the funny colors, those are called analytical lines. Those are actually the structural model layered right on top of the physical model. Okay, so those colored lines are actually what's going to be important and go over to the analysis software. Okay, last thing we need to do over here is I'm just going to put a floor on the top of this. I'm going to do that by picking the boundaries, picking the beams at the boundaries. It's going to be that lightweight metal. And I'll just drop this on here. You see, I tend not to actually, when I have something like this, click on all the individual elements. I tend to trim and really define it with the fewest number of lines I can. But I'm just creating a boundary that's resting on the floor. Okay, so I know that went by really quick, so not that you can sort of repeat it step by step, but conceptually is what I'm doing, sort of making sense of about sort of building up all these different pieces and laying a floor on top of it. Kind of feel okay enough? Okay, don't worry, we're going to go through that in much more detail later, but I just want to show you how you can actually take this towards the whole notion of analysis. And the idea is we really start by building up something like this, and then we actually can start adding information to it to actually make it analyzable. So let me tell you about a few things that you need to do to kind of think about to make it analyzable. One thing we might want to consider is our structure's looking pretty good in here. If we're going to put loads in our structure and start analyzing it, this structure is actually just kind of floating in space right now. It's just kind of hanging out there in the big, wide open space right now. One thing that we need to do for analysis is we need to put something on called boundary conditions, okay, where we actually say, hey, where are those hard parts where the Earth is going to resist and we cannot go any further? Okay, because we need to have a reaction somewhere. So, on the analysis side, we actually do go through and put in some stuff called a boundary, like a boundary condition. All the analysis stuff lives under this area over here called the Analyze tab, and there's some things called boundary conditions here. If I want to add boundary conditions to my model, I'm going to put some at some specific points. And I can put a little boundary condition under each of these. For the boundary conditions, you have the choice of, is it fixed? Is it pinned? you have all these different variations on it. I'm just putting these little boundary conditions. What I'm trying to do is actually just put something there that's going to resist the load so that nothing moves in space. It's like it's actually anchored to the ground and it can't go any further. Okay. The other thing I typically do with this is I go through and I put some loads on. And it's going to sound weird, but even loads are a BIM modeling object. Okay, so in structural engineering, we tend to think about there being dead loads and live loads. For example, us dancing around on top of this floor, we're point loads, but we use sort of an overall average for what our load is in terms of distributing across the floor. It'll be around like 40 pounds a square foot for a residence. It's different for different types of uses. In a heavy-duty storage place, it might be 60 or 80 pounds a square foot. In a library, it's higher, but 40 pounds a square foot is, at least for residential, what we typically assume as a load. So kind of just general purpose people walking around and working. Loads exist here in the Analyze tab too. So I can actually go through and put a load on, and they have different types of loads, including like an area load. So if I want to put a load of like 40 or 50 pounds a square foot all over this entire area, what I can do is just choose that, choose the boundary of the area, and there's the load. I can go through and give it a magnitude in the Z direction. If it was 50, that's kips per square foot. So 1,000, that's like 1,000 pounds per square foot. So a kip is 1,000 pounds. Okay, so if I wanted that to be 50, it'd be 0.005. Okay, kips per square foot. That'll look a lot smaller. And is it a dead load or a live load? Let me make it a live load case. We'll talk eventually about this whole notion of all the different loading cases. And when we do our structural engineering, it's not just the live loads. We consider the dead load, we consider the live load, we consider combinations of the dead load and the live load for all the different sort of conditions in our unit. Yes?
Does it, by like designating it as a dead load or a live load, does it automatically calculate like the different factors? That API?
Yes.
Oh.
Yep. So it's really good about that in terms of by just classifying the load properly and the load cases in the analysis software, it'll do the right thing in terms of all the different load combinations. It's actually very cool. Okay, so we put some loads on there. And at this point, okay, we got a basic structural frame. I got some boundaries. I got some loads. Believe it or not, with that 15 minutes of really quickly rushing through that, we have something we can actually analyze now and start looking at the structural analysis portions. So in terms of where this goes now, we could take it to robot structural, we could take it to E-tabs, we could send it up to the cloud and do the analysis there. There's a number of places we can do that sort of analysis. I'm going to take it to robot structural, which is that application that I have on my machine. Let me send it to robot structural analysis and cross our fingers. I'm going to send the model there. No, I don't want to do that right now. Thank you very much. What it's going to do is take this model that we've created as our BIM model, just adding a little bit of extra information to it, the loads and the boundary conditions, and actually take that and pull out the structural model, send it over to robot structural, and the E-tab link is the same thing. Pull it out. Okay, I'll say no, I don't care about seeing the report just right now. Let's go over to robot structural and show you what it looks like on the other side. Okay. This is what the model looks like over on robot structural. So this is kind of what it looks like in E-tabs also. You have a simple line representation of the columns, you have the boundary conditions, you can show the loads if we want to. But we're ready to actually do some analysis on this right now. So in terms of doing that, let me just say that I want to show some results. We haven't done the calculations yet. I'll say yes, let's go ahead and run them. Let's take a look at what we can actually show now. So if you aren't a structural engineer and this is looking like complete Greek to you, don't panic. Yeah, it will ultimately kind of teach you how to work with this stuff and combine you with some of the structural engineers in the course so you can be familiar with it too. But let me show you some interesting stuff that might be good. For example, moments in the Y direction. I'm very bad about my X, Y, Z's. Okay, so let's actually sort of see what's going on here. for my little two-base system, you can see these are the shear and bending, or this is the moment diagrams for each of the different members. You can start to see what the moment diagram looks like. And if you actually want to sort of have numeric values for all those things, I can say, actually, let's put some labels on there so we can see. I'll just do the local extremes. Okay, so these are the shear and bend, or these are just the bending moments on each of the different members, on the columns, as well as on all the different individual members. So I can see it's minus 22, it's minus 20.35, it's, oh, what is that at the top there? It's showing you the extreme there is minus 77. That's the worst. The worst case right now seems to be, I think it's actually pointing to the middle beam right there where it has things joining from the two sides. It's got a lot of load coming from two sides. So that seems to be the most heavily loaded beam right now. That's the center beam coming through. So we could do things like showing, the reaction forces. If we don't want to, or excuse me, the shear, or the moments. If I don't want to see that, I can go through and show, for example, just the shears instead. Oh, I didn't get that right. I'm so bad about the XYZs. Okay, there's the shear diagrams. Again, for all those different, kind of showing us the different shear diagrams. So again, we can start sizing up our beams and doing our analysis based on that. You can also go through and show things like, the deformations. Okay, now, this is kind of scaled up right now. Kind of rotate that around so you can sort of get a better sense of that. So right now, I have, it's dipping in two big areas right now. That's because these giant 30 by 30 foot bays, I just have beams around the outside. I really need to go back and put some intermediate beams to sort of shore up that floor. But the type of floor that I have in right there right now, and they have these huge deformations, you can't go ahead and have those. So that's telling me I need to put some more beams in here to make it all work. Okay, so we can show things like this. The other thing we can do is, this is all good for like the finite element analysis. So for example, if I want to show some stress maps of how the moments are applying, of how the membrane forces are, whatever it is, I can go through and show these different things, see what the values are. And I can vary these things for the different cases. This is right now just the dead load case. I can change that to be the live load case and sort of see how things change, or different combination cases, a seismic load, a snow load, as many different cases as I want to go through and define. So, yeah, again, this is really getting very deep into the world of the structural engineers. Well, for the structural engineers, I'm just skimming the surface in terms of what's going on here. But the important part I want everyone to carry away with is just that we've been building these models just for the sake of, we think, just doing the architectural design and understanding the space to meet our requirements, but they're actually active, live models that can be used for doing the analysis, and any changes we can make, we can incorporate back into our model for multiple purposes. Yes?
Can you show us later how to take like an architectural model? Like if we take an architectural model and then like detail off of that.
Yes.
Showing how to do that. I don't know if it's
Yeah, that's a very good thing. I think we were talking about just really the flow for the next couple of classes. That'd be a very good sort of next step to really get you into that. Okay, you did what I always call the design development, the early stage. Let's take it down to that next one of really adding these detailed systems and also pulling it into the real construction details. So we can really show you just how you slice and dice this and add the annotations to really make it a full construction set. Okay, now that's where we're going. Excellent.
Can you define the connection of the beam and the beam and core? Because sometimes they can fix.
Oh, exactly. So let's go back over to the Revit side and just show you where that is. You could do it in the analysis tool, it's too, but let's just go over to Revit. For each of these different sort of connections, let me see if I can get back to the structural model here. That's the analytical beam. We can actually start for each of these different things talking about the end conditions. Is it pinned? Is it fixed? And really, we can set up moment frames or simple connections, shear connections, moment transferring connections. Yes, you can do all that in the analytical model, and that'll make a very big difference in terms of how the analysis comes out. I didn't change any of that stuff. I just live with its kind of standard connections in here. The way this is going right now, you know, if you think about this as the way that I define this by default, the columns are sort of like anchored in concrete. They're not moving. Everything up here is just pinned. So all the stress is really getting carried down to that big fixed connection. That's why we have these big moments in the columns. But if I started locking some of these connections up here, yeah, you'd have a very different profile because they'd be absorbing a lot of that and it wouldn't get torqued down to the bottom. So right now, yes, our columns are carrying a lot of sideways stress because the only lateral resistance is coming from the base. And yeah, that's not a good design, but that's what it does by default. Okay. So let us go ahead and adjourn for the night. Again, that's just sort of a preview of where we're going. So keep focusing on the architectural side for now. Get these models finished up. We'll talk some more about creating custom pieces, but as we're talking about how to do cooler and cooler things architecturally, we're going to go off on this other path, which is more and more about the analysis and how you really get to do more and more detailed construction drawing at the same time. Okay, so kind of forking here and really going to start building up your power in 2 dimensions.